Thank you very much for having me. It's a real privilege to be here. I'm A.FRANKLYN Miller. I'm a sports medicine physician, and I'm very proud to be the director of sports medicine at this place in Dublin, Ireland. We have 7 operating theatres and 70 beds. It's a purely private orthopaedic hospital, been open for 10 years. And the image on the bottom is our new sports medicine facility, which really is fantastic. We see 40,000 patients a year in that from a rehabilitation and biomechanics perspective. But we're very fortunate in having a board who allow us to continue on with research. And so one of our major tenets, although it's a commercial clinic, is to look at data of those patients as we move. So we're talking about ACL today, and as we know, we all work in those patients. We look after them, whether we operate on them or whether we rehabilitate them or return them to sport. And we think we're pretty good at it. Do you know, that's why we're all here. But we can see from Claire Arden's work here in 2014 that actually, even though we think we're very good at it, actually our patients don't really bear out with that. So we can see that 65% return to a sporting activity, and it's arguable whether 50% actually achieve a full return to competitive sport. So when we look at that ourselves, are we doing something wrong? Or is there really an opportunity to try and make things a little better? So I've been asked to talk about biomechanics, and so obviously I'm going to try and take you down that journey. But can biomechanics add value to this process, or really is it just adding a layer of complexity in order to either sell something or to provide people jobs in terms of analyzing the data? Well, what is biomechanics? Biomechanics started with stroboscopic images. Indeed, the first commercial camera at 1,000 frames per second was French. And really, this has allowed someone to break down movement into numerous parts, but didn't give an ability to quantify anything. Obviously, we can move on from that into digital motion capture systems by using multiple cameras and embedding those with force plates. We can start to get an idea of how we can create joint angles in multiple planes, but also joint loads in terms of kinetics. What that really means is we put reflective markers on bony landmarks so we can define a segment of joints, and then we use cameras in order to track those markers through a typical movement. So we can apply that to various movements as long as they're reproducible, and the cameras can give us joint angles, and force plates in the ground can give us joint kinetics, so the forces across those joints. And we can do that in real time, but the data itself needs interpretation afterwards. So this isn't video, it's really taking numbers and mathematically looking at the movements that our patients obey. But the work we're doing isn't new. There's actually a lot of publications on this. This is a famous publication from Tim Hewitt's group looking at a double leg drop landing to see whether or not in a group of female patients, we see 200 or so subjects, whether or not that biomechanics can predict ACL injury. And this paper, well cited, suggests that in a group with an ACL who went on to develop ACL injury, that the knee abduction angle was 8 degrees greater as assessed using 3D. The ground reaction forces were higher, and the knee abduction moment, so the force going through that abduction movement, was 20% greater. And then looking at the rock curve, you could see the 78% sensitivity. So job done. Biomechanics works, does it not? Actually not. So Trond Kroshaug's group from Oslo did almost the same experiment, looking at a double leg drop landing, and then in their rock curve found that actually knee valgus, or that knee abduction moment, wasn't predictive of ACL injury. So how can that be? 2 big groups, 2 established groups, identifying the same variable, one predictive, one not predictive. Well, it goes on, and I could cite any number of studies. Paterno, another huge biomechanics group here, did a smaller subject with 50 or so female participants and found that it wasn't so much the knee, it was more the hip. And we could go on and on and on. We could pick any biomechanical group who've looked at ACL deficiency and identified a certain variable. So what's wrong with biomechanics? Is it that it just doesn't add value, or can we look at it a different way? Well, typically what happens when we decide to look at biomechanics is we look at a variable. We choose something to look at. Might be peak knee flexion, might be peak ground reaction force. Chris Richter, who works in our data science team, wrote this paper looking at the whole waveform. So if we look at a counter movement jump and we look at the data curve there of both ground reaction force and center of mass displacement, if we decide to look at discrete points, you see on the screen, we can only see a very small part of the data. And we channel what we're looking at into that data beforehand. With continuous wave analysis, we can take away the blinding of that data and look at the whole wave. It takes more in terms of mathematical processing power in order to do that, and it takes longer in time, but it exposes the whole trace. So that might be one of the deficiencies. The other deficiency is, of course, that things change. This is a nice paper in a simulated soccer match, which took a number of participants and looked at a drop landing throughout a simulated match in terms of fatigue, and identified that actually as time went on, we see that those biomechanical variables change. More knee valgus, more hip internal rotation, more ground contact time. So if we pick a certain moment in time, as well as a certain variable, we can see that we could blind ourselves to the wealth of available data. So is it so much that we're not looking at biomechanics correctly? Are we trying to identify predefined movements? And I'm speaking tomorrow on groin pain. I'm going to talk a little bit about clustering of data tomorrow. But this is a brand new paper in the Scandinavian Journal looking at runners, 300 or so, who were injured and uninjured. And the idea was to look and see if there were biomechanical variables could predict or identify those runners who may or may not be injured. And what they found was actually that the individual variables can't predict, but that runners fit into one of 5 clusters, or this group. So by taking multiple different variables and trying to use a machine learning model to identify variables that are common across patient groups, we can start to identify a trend or a shape by which we can assess risk. So can we use that machine learning data to find out differences between groups? I'm going to present our work in a second, but it's been done before. Ross here looked at the differences between elite athletes and recreational athletes and asked them to perform a number of movement tests. There are a lot of tests, a lot of subjects, but they could identify reliably, 70% or so reliability, whether an athlete was elite or whether it was novice, performing the same test using code. So of course these subjects are real, but the researchers aren't looking at the person, they're looking at the data. So we're fortunate to have a very large data set. We look after 900 or so patients each year following ACL reconstruction. Our database is well over 5,000 patients at 3, 6, and 9 months after surgery. So we're able to combine multiple layers of tests. We published this paper this year in PLOS, and I'm going to spend a little bit of time talking you through how the machine learning code starts to identify critical variables. So we took 150 or so patients at 9 months post-operative ACL, and we compared that to a smaller control group. And we put them through a battery of tests: single leg, double leg counter movement jump, single and double leg drop landing, a hurdle hop, and then planned and unplanned cutting. So we had a wealth of data on those subjects. Each patient had the control limb, the unoperated limb, and the operated limb. And so what we then did was go through a set of sequences. Now I'm going to talk you through this in terms of number 1 and number 2. So the first thing was to pool all of the data of the patients who had an ACL injury and pool all the data of those who didn't. And then of all of the tests of the biomechanics, we looked for commonality. So if anything discriminated against being injured or uninjured, we kept the data. If it didn't discriminate, we discarded the data. So you can see here 2 lines, we retained about a quarter of the features. So 3/4 were non-discriminatory. They were the same variables. And what were those variables? They were the joint angles at the hip, the torso, the knee, the ankle, the foot. There were loading forces in 3 planes at all of those joints. There was center of mass displacement. There was ground reaction force and impulse. So we put all of the variables together. We kept about a quarter of them. And then we had to select a machine learning mechanism which could reliably sort the remaining data into ACL reconstruction or not. We use a number of different machine learning codes. Bottom right-hand corner demonstrates fit. And so we ran through those methods of machine learning that identified correctly the membership of the group. Regression analysis, you can see there at the top for the single leg counter movement, the double leg counter movement, the hurdle hop, and the single leg hop identified more correctly. So we used regression analysis in order to fit that data modeling. The next thing was to try and use the features of the smallest number of fit. So rather than use every feature as part of the test, which tests and which variables of those tests could we minimize the model to? Why is that important? Because it's speed. The longer that it takes, the more variables we input, the harder it becomes. And then, so we started to work through that. We found that the double leg drop jump is certainly the more discriminatory of the tests, and you can see that highlighted there. But what does that really mean? So if you focus on the bottom left-hand corner, that little grid there looks at the percentages of correctly identified patients from the model. So 23% were correctly identified by the model as having had an ACL operation. 24% were correctly identified as having no operation, but having been an ACL patient on the other leg. And then 27% were identified as being normals or controls. Now, of course, there's error in that model. So 70% or so accurate prediction of the model of which group membership. But we don't know whether those errors are based on a normal population being at risk of an ACL injury. So this isn't predictive. But what we can say is it allows us to form groups. So the clustering allows us 70% accuracy of cluster membership. And what that does is we can start to treat it as a safe zone. So rather than looking at that knee valgus mechanism as being the all-important variable, we can find a cluster of features which put you either in safe or at risk. And of course, there are multiple ways of arriving within that safe zone. So it might be you don't need to work on a specific variable, but you take the whole and you can work and rehabilitate based around the aim to get back to that cluster. And it makes sense of using all of those multiple data points. And we've gone on to check this. This is unpublished work. We've taken our model and applied it to the Oslo sports trauma data. And obviously you saw earlier that Tron's publication found that the double leg drop landing, when looking in discrete point analysis, didn't find knee valgus as a movement. And you can see the rock curve there on the right, which suggests, again, similar sensitivity of our model to their data. But that's interesting maths, but how do we actually use it in terms of return to play decision making or in terms of tracking rehabilitation? So our patients following rehabilitation go through a 3-step process at broadly 3, 6, and 9 months post-operation. So at 3 months post-operation, they do a set of isokinetic dynamometry tests and then jump and power tests. And then at 6 and 9 months, they repeat those and add in running and change of direction tests, all using 3D biomechanics. That allows us to both track that rehab, but then use our cluster analysis to start to shape them towards where they need to go from a rehabilitation point of view. And we're working with partners to look at some of the data individually, obviously isokinetic dynamometry, jump testing, running, in particular working with Peter Weyand in Dallas. And then change of direction. But of course, not everyone has the opportunity to come to a laboratory. Our patients are very fortunate, but willingly take part in this as research. But we'd like to be able to take that to the field and really our main focus this year is to make this available outside of the clinic. Because when we look at return to play field tests, there are many of them, but really their output is time. So when we ask a patient to undergo either the Illinois or the 505, you as a rehab staff or a club staff, a club doctor, get a number, you get time. And so it's very difficult to reproduce that, or you can reproduce it in multiple ways. So we've been trying to take the machine learning analysis on our patients as we track them through rehabilitation to design a field test which takes those risk exposure variables in a test we've called VU. It's called VU because you run a VU shape. So you start with a hurdle hop, which we've used as a discriminatory marker, and then you run a V, which is a 110-degree cut. You backpedal one of those limbs, and then you do 2 curvy linear runs around the same group, and then a 20-meter sprint, just as that little screen demonstrated. The publication here in Sensor just has taken the inertial sensors we're using, and we've partnered with XSense, who are pretty much the global leader in inertial IMUs. And we've compared that to gold standard lab data. So our Vicon camera units have tracked the analysis. And you can see this is just some of the early data processing. You can see on the left-hand side of your screen the VU track measured by the inertial sensors. And obviously the inertial sensors don't know where they are necessarily, so they need to learn that it's reproducible in the field. And you can see the error measurements on the right-hand side. So we're very happy in a sagittal plane, and we're not too unhappy in a frontal plane. Where did that come from? Well, much as I've just spent some time explaining the machine learning, across both our ACL rehab and groin rehab, we looked for the most discriminatory markers of tests, not because there's any one measure on its own is all important, but there are certainly features that are important across all of these to push patients in or out of safe zones. And so we think that perhaps this might help that rehab process and help describing the return to play mechanism in a field-based application, which will provide access both to that algorithmic data, but also to the hard data itself in terms of joint motion. So what does VU aim to do? Well, it aims to give both time, joint accelerations, and joint angles for each phase of that test. So backpedal, curvilinear run, maximum velocity on a sprint. And to take those features that we've exposed as risk features or unsafe features and allow you to look at them realistically. It will allow us to compare both the player or the patient in an injured state, a return from injury, and in an uninjured state. So we'll be able to see, although you'll have ultimately a time, we'll be able to see whether or not you've achieved the same time in a different way. And it will allow us to track changes throughout a season. And really the goal here is, the longer term goal is using artificial intelligence. It may allow us to start to be predictive, because what we've done so far is really retrospective observation. So we can observe the cluster membership of different groups and the various risk factors, but what we can't do is say that those risk factors are risk factors for future injury as opposed to current group membership, but certainly allow us to identify the attributes of which a patient is safe. And so let me just summarize there in terms of the role of biomechanics to date. So the evidence has shown that single biomechanical variables are probably not that useful. There's too much of a mixed message. So if you pick and hang your hat on one variable, you're likely to go wrong. We can use PCA modeling to try to look at multiple variables at the same time and cluster them together to form a pattern of risk versus lower risk. We're working very hard to try and reproduce as much of those variable feature selection in the field as in the lab. And the difficulty in taking that one variable and hanging your hat on is it makes rehab very prescriptive. Whereas if you have multiple features and you put them together as a cluster, it makes rehab much more variable and explains often why therapists will work in different ways with different athletes to get the same result. And so this is not a sort of one-size-fits-all, it's a trend towards focus. So the real answer is there of use? Of course there's of some use. Is it widely available and applicable yet? Not yet. Is discrete analysis the way to go? No, clusters are probably the answer. Of course, there's a huge team. You're going to hear from Enda King now. Chris Richter is our data scientist and runs a department in terms of writing the algorithmic code. And one of our first PhD students in this was Shane Gore, who's done a lot of work on variability and movement complexity. And our lab runs via a huge number of ever-rotating one-year interns, some of which are part of the data collection here. And I have to give great thanks to them. And thank you all for listening.